Yeah. So if you don't know how to do the tutorial, especially the later chapters, right? Don't be panic, because sometimes the tutorial now, for year 2 onwards, the way we're going to do tutorial is not a reflection of the exam question. Even in textbooks, right? In fact, most of our tutorial in this course are taken from various textbooks that cover the same chapter, and sometimes they just purposely choose a question to illuminate certain extra new things, and some interesting thing to discuss. And some of these questions, there's no way that's going to appear in the exam. For example, tutorial 5 tutorial 5 question 1 is asking you to list a lot of energy levels, right? So even if it's in the exam, it's going to be a shorter version of it, and sometimes the question also takes a long time to calculate and things like that, and so on and so forth. So it's not in the it won't be like what we will do in the exam. Okay, so I guess now what we can do is we're going to continue to finish off this discussion about the Larmor precession. So I guess there's one way to think of it. Yeah, so for question, definitely not too late to start now. It's still like a few more weeks before the end of the semester. 3 more weeks? Yeah, I guess so, about there, right? So I guess the idea is, I think if you feel like you understand the lecture is gonna be pretty good already, right? So sometimes tutorial are purposely challenging, okay, because the textbook and sometimes me, I want to show some weird phenomena to outline in the tutorial. So I guess, yeah, so I guess that's the thing. I guess we will talk more about tutorials later, but what we're going to do now is to talk about the Larmor precession. So just to try to remind everyone what we are talking about for the Larmor precession. We are talking about a particle with a spin, right? If this particle has a charge, right? So if this thing carries a charge and it is spinning, it is going to carry some kind of magnetic dipole moment, right? So magnetic dipole moment, something like that. Okay, so roughly speaking, like this. And then what we are going to do is we are studying what happens if this object is placed in a magnetic field in the z direction, and we just in this chapter we will study the simple case where it is just a constant along the z direction. So where we left off in the previous class was we constructed the Hamiltonian. So I have give you the reasoning why the Hamiltonian looks like this. The result that we got was half h bar gamma. Gamma is the gyromagnetic ratio, and it is sigma dot product with B. Okay, so if my magnetic field is purely pointing in the z direction, then sigma dot B only just give you the z component. So it's just B is a constant, so it just tells you how strong is the magnetic field, and it's going to be sigma z, right? So sigma z, if you recall, it is our Pauli matrix in the z direction, so 0, 0, minus 1. Okay, and our Hamiltonian is just a constant times the Pauli, so the Pauli matrix. So it's gonna be pretty fast to solve the Schrodinger equation, because we already know what will be the eigenstates of the Hamiltonian. It is the eigenstates of the Pauli z, right? So these things are the eigenstates. So therefore we got the solution. We can give you the energy level. So let us recap what are the energy levels first. So this is the eigenstate, right? It is because this is just the operator. These are constants. So what we have here is just half gamma B0 sigma z operating on this, and this thing operating on this just gives you back the up thing again. So it's just negative half h bar gamma B0 up vector, right? So this, according to this equation, this is my eigenvalue, and we call this E plus. We are just following the Griffiths notation. E plus is a negative energy level, so it's gamma B0, right? So this is the first, and this is this eigenstate. And if my spin is spinning down, right? Instead of pointing up, it's pointing down. If I add this on the down state, because this is the eigenstate of sigma z operating on this just gives me a negative, right? So the eigenvalue that we got minus minus becomes a plus. So I got half h bar gamma b0 spin down. And this is the eigenvalue. So this is, let's call this E negative. And E negative is plus h bar gamma b0. Okay, so these are the energy levels of the particle of a spin inside a magnetic field. So like I was saying previously, this is a simple situation, but it's actually, because it's simple, it actually covers a lot of phenomena, like the paramagnetism that you learn in statistical mechanics, or like magnetic materials. So how come magnetic materials, certain materials, if you put it in a magnetic field, the thing itself becomes magnetized, right? You can play this in, even you have played this at home also. If you have a magnet, right, and then if you put a paper clip on the magnet, the paper clip temporarily becomes a magnet itself. So the paper clip itself can attract other metal objects, and this is a process of magnetization. Okay, so this is captured in this phenomena, and then later, if we are able to solve, we are not going to do that now, but if you consider the case where the magnetic field is changing with time, then this is how your MRI machine works. Nuclear magnetic resonance and magnetic resonance imaging, right? So if you go to the hospital for a certain condition, you need to scan your brain or you scan your body, right? And then you lie down into the machine, and then you must take out all your metal objects, right? You must be naked, or you wear only the clothes, cloth, no metal. Because there's a magnetic field, right? And then what you do, the machine does is you put your body in a magnetic field that that is changing with time up to a certain frequency. And by detecting, because when they do this, right, they temporarily affect the spins of all your body. And once you turn off the magnetic field, all the spins in your body will relax back down into its low energy state. And if you can measure, if you can detect when it goes to a low energy state, it will emit photons. And if you can detect and measure the photons, this is how you can scan your brain, basically, right? At the end of the day, right, after all this complicated process, you can actually scan your brain without opening your body inside. So that is a very useful applications. Okay, so that's why in another possible jobs that people can do in physics after graduating physics is working in hospital, because all these MRI machine are physics kind of things. So you need some physics knowledge to do that. Okay, so let's see. So now that we got this kind of motivation, so let us try to solve this equation. So let us consider initial state, right? So since we know that up and down are the eigenstates, so any other state can be constructed as a linear combination of the ups and downs, right? So linear combinations of all this. Okay, and what we're going to do is I'm going to make a choice of the A and B. Because A and B, right, the mod square are probabilities. Okay, let us choose, because we have a something square plus something square equals to 1. So what if we choose this to be a cosine and sine function? Then the square equals to 1. Right, so this is one way to parameterize your state. Okay, so if you are reading up about the Bloch sphere and things like that, because some of you are asking, right, this is like kind of something similar, almost, but not yet. But let's focus on this part first, right? So basically what I'm saying is my initial state is just cos alpha over 2 up, and then sine alpha over 2 down. Okay, so this is the state at time 0, and these are the eigenstates of the Hamiltonian, and we know already at time greater or equals to 0, then what happens to the state at any time, any later time, initial time? If these are the eigenstates of Hamiltonian, we immediately know how to write the answer, right? It's just the exponential of I and the corresponding energy levels, right? If you forget why this is the, if you, wait, let me write first before I say, the energy level is E plus up, and then sine alpha over 2, energy level I E minus T over H bar down. Okay, so if you forget why this is the case, actually don't worry, because when we start the next chapter, we will repeat again this reasoning. So yeah, but in any case, E plus and E minus is something that we know the expression of is over here. So let's write it out. Okay, so it's just E. E plus is there's a negative, so it becomes a plus I, and then there's a 2. There's a H bar, but it cancels the H bar, so it's just gamma B T over 2, right? So I got this, and then this is a sine alpha over 2, and then this is negative, so it's just e to the negative I gamma B 0 T over 2. So we got that already, right? So this is my state at any time t. So it depends on what is your initial condition. That means depends on what is the A. Once you've chosen the A, the B will be determined by this, in the case where they are real numbers. So this is a special case, right? Remember, A and B could be any complex number that satisfy this, but for the case where it's real, we make this choice. So we are focusing on a specific special case. Okay, so I hope everyone follows so far. We haven't done anything special yet. The next thing that I want to do is just, okay, this is the ket. So let's take the bra. So the bra is the complex conjugate. Okay, and I was saying that we are focusing on the case where the coefficients are real numbers. So the only complex part is here. So it's I gamma B 0 T over 2 up bra, and then I got sine alpha over 2 E, and then take the conjugate, so it becomes a plus now, and then this becomes the bra down. Okay, so we are going to use this to calculate some expectation values. Okay, so does everyone follow so far? Mission Impossible 8. Speaking of which, Mission Impossible 8, the actual movie is coming soon, right? Three more weeks. Didn't even start assignment. Oh, I mean, if you're talking about physical class, hopefully next long sem we open back physical class already. If Wolverine goes into MRI, good question. I think the Wolverine clause is not metal, right? So, oh no, it is metal. Yes, he can't go into MRI. If you remember the first movie, the Magneto can like move his body using magnets. Oh, 7. Yeah, 7. Correct. Yes, just a preference. Yeah, capital. Usually when I write the capital is because to tell the difference between when I go to the position wave function, right? And then this one is just e to the IET over h bar, and then the psi of the position wave function of the nth energy level. So yeah, don't worry, it's a preference. So yeah, 4 is Ghost Protocol, 5 is Rogue Nation, 6 is the most recent one. So no, 7 is the one that haven't come out. Yeah, you're right. Anyway, let's calculate the expectation values. Of what? Well, this whole chapter is talking about the angular momentum, right? In particular, this is a spin. So let us calculate all these things. Okay, so that means I got a spin, but you know, if you want to measure a spin at arbitrary thing, like the MRI machine is like measuring the spin in your body in some sense, although I'm not very sure how it works precisely, but it is the kind of thing that we're dealing with, right, in one way or another. So how do we calculate the expectation values? And what is this? Well, we have shown already, right, that our spin operator is just h bar over 2 times our Pauli matrix, right? And what was the Pauli matrix? So for sigma x, if you remember what we derived this last time, I'm going to use the ket bra form, because you can use the matrix form if you want, but this is also another preference. It's just more fun to play with bras and cats, right? For sigma y, is the same but with the I. So one of them is minus I, one of them is plus I. Okay, and then as for the z direction, h bar over 2 sigma z, sigma z is equals to up up minus down down, right? So you can write this in matrix form if you want, but yeah, it's just more fun to play with bras and cats. So what I want to calculate is, let us start with calculating what is the expectation value of Sx. That means I want to calculate for the state, right? That means at any time t, okay, doesn't have to be time 0, but if I want to calculate the expectation value at some time t, I need to perform this calculation. Okay, so the first thing that we need to do is, well, let us start by calculating this. So what is sigma x times acting on the state here? So the state here we have already found, right, to be over here. So I want sigma x acting on this, right? I don't know if it's clear enough to see. So sigma x acting on this state, so I'll just write this straight away. Okay, so sigma x acting on this, so the first term is the down. So the down will be 0 if I do here, but if I act on here, it will become 1. So it gets it will become sine alpha over 2, right? E minus I gamma b 0 t over 2, and then act down, it will disappear. I'm left behind with the up, right? And then after that, the sigmas, there's still another term acting on this state. So this term acting on this state is the up. So you got cos alpha over 2, e minus I, I gamma b 0 t over 2, right? Up acting on up, left behind with the down vector. Okay, and then the next step is just to find this. So if I close with the bra, right? So now I do this with the bra, right? So the bra is up and up, so I got a sine cos, right? So cos alpha over 2, sine alpha over 2. This thing multiplied by this thing, the exponential over 2 will, the half will disappear, right? And then down acting on down, so down acting on down, it becomes sine cos, and then this times this, so it's just e I gamma b 0 t. Okay, so now I can try to simplify. Well, both terms have cos and sine, and then it is just e to the I gamma b 0 over 2 plus e minus I gamma b 0 t. Okay, so notice that this is an exponential plus the exponential to the negative I. So I can, well, this will be simplified if I put a half and half here, because this is just by the trigo identity, it just becomes sine alpha, right? And this by the identity, the Euler formula, is just the cos of b0 gamma t, right? So in fact, so that means what we have found is the expectation value of sz is h bar over 2, the expectation value of the poly x, and it's just this thing. So it's just h bar over 2 sine alpha cosine gamma b 0 t. Okay, so the expectation value is changing with time in a cosine function for the x direction, and then there's sine alpha is a constant depending on your initial state of your spin. So now that you get the idea, we can just quickly continue to calculate the sy, right? So sy is, yes, we still want to calculate the same state, therefore it is h bar over 2 sigma y psi t over here. So we start by calculating this first. What is sigma y acting on psi t? Okay, so my sigma y is negative I down, acting on down is here, so I got negative I sine alpha over 2 e to the minus I gamma b 0 t over 2, and then left behind with up. Okay, and then the next term is plus I, and then up left behind with down, so the up term will merge with this, so I'm left behind with cos alpha over 2 e I gamma B0 T over 2. This is the down state. Okay, and then you close this with the bra. Right, so my bra is over here. Okay, so up and up gives me a negative. Did I make any mistake? Should be fine. Up and up gives me a minus I cos alpha over 2 sine alpha over 2. Both are the same power, so I square this, so it just becomes I gamma B0 T, and then there's a I sine cos, and then E, so E I gamma B0 T. Okay, so this one also can be simplified. There's a negative, there's an I forgot the I, so everyone has an I factor, and then everyone has a cos alpha over 2 sine alpha over 2. So what I have here is, after I taking this out, this is I gamma B0 T minus E I gamma B0 T. Okay, so this one is also something familiar, because this one is, I can do this, right? If I plus and minus, if I add and multiply and divide by 2i, so that this part I times I becomes a negative, right? And then 2 sine cos is just sine of twice of the angle inside. Do you agree? And then this one is the Euler formula. This is the Euler formula for sine gamma B0 T. So we have found the expectation value of the Y operator is h bar over 2 of what we have just found. So it's negative h bar over 2 sine alpha sine gamma B0 T. Okay, so we got two of them. One of them depends on cos, the other depends on sine. Okay, so it seems like a rotating vector. Okay, we can start to recognize this already. How about the expectation value in the... Am I recording? Yes, I'm recording. What do you mean, the Mission Impossible? Oh, Mission Impossible music is very distinctive. But over the years, there are many different versions, right? So we are at page 3. So one more thing to calculate is sigma z. So Sz is the expectation value by doing h bar over 2 sigma z psi of t, right? So we do the same thing as before. We find what is this. So sigma z acting on psi of t was what? So sigma z is up, up, down, down. Okay, so this part is a bit, I guess this part is easier. It's just this with a negative of this. So it's just cos alpha over 2 e I gamma b0 t over 2 up, because it's an eigenstate, right? And then the second term is an eigenstate with eigenvalue minus 1. So I got a negative sign up here. And I got a sine alpha over 2 e minus I gamma b0 t over 2. This is the down state. And therefore, if I close this with the bra again, right? So I take this whole thing, I act on here. So acting on here, it just gives me, the first term is just cos square alpha over 2. The exponential cancel each other, so it becomes 1, right? And then the second term is just sine square alpha over 2. Exponential times the other complex conjugate exponential, it just disappear, becomes 1. So it's just cos square minus sine square alpha over 2. So cos square minus sine square is what? It's just cosine of the double of the angle, right? So therefore, we have found the last one. The expectation value of Sz is just h bar over 2 times the expectation value in the Pauli. So it's just h bar over 2 cos alpha. Okay, so yeah, we are basically done already. Now it's just to look at what we have found. So let us collect our result. We have found the components. So we, in fact, therefore we already have the expectation value of the of the spin angular momentum vector, right? And it's also reflecting the fact that this is constant, right? So this is constant, right? So consistent with the fact that it is the eigenstates of sigma z, and therefore the eigenstates of h. Okay, so in any case, what we have here is, let's see what we have. So the expectation value of the spin angular momentum vector is what? Well, let us see what we have. So remember, what is our angular momentum spin? So the spin has xyz component, so I got sx, right, in the I direction, and then sy in the j direction, and then sz in the k direction. And what we have found are the expectation value of each of them. So expectation value of each of them, it will give us a picture of what will happen to this vector. The expectation value, right? It's not a specific point, but when you do measurement case by case, you might get different result up to a probability distribution, but the expectation value of this distribution will be given by all these quantities. So we have found all this already. What was Sx? We have found it to be h bar over 2 sine cos, right? So this h bar over 2 sine alpha cos gamma b0t. So this is in the I direction, and then the sy is negative h bar over 2 sine alpha, and then sine gamma b0t in the j direction, and the last one is a constant of cosine alpha, right, in the k direction. Okay, so that is basically our result, right? So notice that this one, I hope you remember something similar that we did in mechanics. My x coordinate depends on cosine something, my y coordinate depends on sine something. So this is a circular motion, right? So the vector here is rotating in the xy plane, right? So I got a cosine and sine here. So this part is rotating, and in fact, if you look at this, this is my angular velocity. So this is a rotating about angular velocity, not about with. Gamma is omega is gamma b0, right? And this part here is just a constant. Okay. Yes, back to spherical coordinates, right? Well, we are like pointing the angular, plotting the graph in 3D anyway, right? And in fact, what is the length of this vector? Can you tell? This thing square plus this thing square. So this thing will become 1. So it's just sine square with h bar over 2 plus cosine square. So the length of this vector is a constant and is h bar over 2. Can you see? Right? I'm lazy to draw this line because what I want to do now is to just start drawing this. Okay, so the length of this vector is a constant, which is h bar over 2. So let us draw a vector of length h bar over 2. So that means the whole vector is contained inside this, on the surface of this sphere, where this part is h bar over 2. So this is my sz direction, this is my sx direction, this is my sy direction. So this is h bar over 2 over here. Okay, and then we notice that the z coordinate is h bar over 2 cosine alpha. So maybe it's, I don't know, is it somewhere here? Let's roughly speaking, h bar over 2 cos alpha. So that means my vector is here to here, right? So the length, the full length is h bar over 2, right? But it's cosine alpha, so in fact this is alpha. Can you see? And then the x and y coordinate is precessing. So this is a rotation about this axis. So if you just project this down to the xy plane, you can see the shadow of this picture. It is just a circular motion about the xy plane. Yeah. Right. So this is my vector of expectation value. So I'm talking specifically about expectation value, right? The vector itself is something we discussed last time, but see, because this is an eigenstate of z, so it's the z component is definite, is fixed, so that is fixed, but the x and y component is not fixed, it is changing with time, right? So in fact, let us draw the top-down view. That means we draw the x and y coordinates only. So if I just draw the x and y coordinates, what do I get? So sx, sy, right? It is rotating, right? So this represents the equation of a circle, and what is the length, what is the radius of this circle? H bar over 2 sine alpha. So the length of the h bar over 2 sine alpha, right? So you see, if you project this down, this length is h bar over 2 sine alpha, right? And my vector is rotating, so this is plus, so this is a positive x coordinate, this is a negative y coordinate. So like maybe like this, right? At time 0, it will be pointing perfectly to the left, but as time increases, it will be like this. So the angle here is gamma b0 t. So as time increases, this angle will rotate, right? So this vector here is actually rotating about the axis in this direction with angular velocity omega, right? So let me write down what I just said. The vector, the expectation value of this vector is this behavior, right? Maybe you use this word in theoretical mechanics already. We call this precessing. Okay, precessing about the z-axis. And in fact, we have found that the angle is alpha, because see, it's like precisely the component is cos alpha, right? Z cos alpha at angle alpha, and angular velocity, which is given by omega. See, this part, the coefficient of t is our angular velocity, so it's gamma b0. Okay, so this angular velocity is something that can be measured, and this b0 is something that you can control in your experiment. So this is one possible experiment to measure the gyromagnetic ratio of a particle, if you can measure the expectation value and see how fast does it precess. So it would be a difficult experiment, because a spin, right, is a small particle, and then you need to put a magnetic field, and you need to detect the expectation value of the spin. So probably not an easy thing to do, but it's possible, and these are one of the ways we can say that, yeah, this is one method to measure the gyromagnetic ratio. But this omega here has a name. We call this the Larmor frequency. Or the Larmor angular frequency, right? Just divide by 2 pi to get back your ordinary frequency. So like I said, the application of this is like you can use this in MRI, right? NMR, and so on and so forth. Okay, what time are we at now? Yep, still pretty early. Does anyone have any question? Okay. Firecrackers specifically. Is it because in Mission Impossible they always start with they light a fire, right? Then they light a fire to a wire, and then the fire will go along. Okay, so that was our final topic on angular momentum. Even though you say quite fast, it feels like we spent quite a long time in chapter 6, right? Remember what did we started with? We started with orbital angular momentum. We tried to find the eigenstates, and then after that, okay, we find the eigenstates, and then we try to get the interpretation that they are actually spherical harmonics. After that, we start talking about spin, right? And then we recontextualize the spin. Now we derive, so the Pauli matrices are related to spin half particles, and we recontextualize our Stern-Gallac experiment using that. And then now we know that, okay, the operators that we were using at the beginning is actually what we're doing here is actually the spin angular momentum. Okay, and then now we apply this knowledge to the Larmor precession. So yeah, so I guess that's about it. Since if there's no other outstanding issues, we shall go to chapter 7. Okay, so chapter 7 is about operators. Okay, and we call this operator formalism. Just a fancy name. It just means it just means we are talking about operators in this chapter. The first thing is just a brief discussion. Just now, remember, like I said, if you forgot how come the initial state, if I know that these are eigenstates, if this is the initial state, then immediately after that, at any time t, I can jump to this. So we will explain again here in a bit more detail. So this is 7.1. And this is the title of this section is also another fancy name, the Hamiltonian as a generator of time translation. Okay, time translation and time evolution means the same thing. It just means that you are moving the system forward in time. Okay. So this is a bit of a parallel to what you guys, from what I understand, what you guys are doing in theoretical mechanics already, right? Because in theoretical mechanics, and here both cases we are dealing with functions of time, and then we need to differentiate with respect to time. But sometimes it will be, there's an important distinction when we differentiate, right? Is it just differentiating a mathematical function? Or if you are differentiating a function, when the function changes, right, does it evolve dynamically? Okay, dynamical evolution. So dynamical evolution means the system is changing based on the physical properties of the system. It's not changing based on your constraints or how you define your functions. That is external. Okay, the dynamical evolution is the system itself doing physics. Okay. And the dynamical evolution of a system for quantum mechanics here depends on the Hamiltonian. So the Hamiltonian controls how the system evolves. And this is what we want to study in a little bit more detail. And it's going to be a bit more, slightly more mathematical, but it's nothing new. Okay, nothing new. In fact, we write down the position wave function using our usual formulas. So let us start. Like, let's say I have some state. So let us start with my quantum system at any state psi of t, right? And its position wave function is, well, remember, right? If I want to, from the ket, this is a ket. If I want to find the position wave function, that means it's going to be a function of x. So you do this, and then it will become this as a function of x, but obviously because it's a quantum system evolving, right? It's a physical system, so it changes with time. So there's a function, it depends on t as well. Okay, so see, we are not doing anything new. And the next thing I'm going to do is also nothing new. You have done this in calculus already. We are going to perform a Taylor expansion. About center. So let's say I perform at some fixed time t0. So we're not doing anything special. It's a function of t. So let's do a Taylor series, right? So that means my wave function here is a Taylor series. So Taylor series, you sum from 0 to infinity, right? And then 1 over k factorial, right? And then you differentiate the function k times, right? So differentiate a function k times. After you differentiate, you evaluate the value of your derivative at your center. I hope you remember this. And then x minus, Taylor, this is t, right? We're expanding about t, so t to the power k. Right, so Taylor series fx is equals to a summation k 1 over k factorial. You differentiate this k times, you this, and then x minus x0. So I hope you remember this. Right, it was calculus 2, or was it 1? And what I'm going to do is I'm going to rewrite in a more operator language, because this term means this means differentiate k times. So I'm going to write this instead. And then evaluate at t. So I'm just writing in this form. Right, so if I just treat t and then I just evaluate, and then if I substitute back t0, so it's just the same thing as doing this. Okay, so what we have here is, that means I can write this as an operator form now, because this is a chapter about operators after all, right? And I want to see what is the derivative operator associated to this problem. So this is a summation from k0 to infinity. Let me just move this to here. And then this is just differentiating k times and acting on this operator t0. Okay, so again, I'm not doing anything special. It's just things you have seen before, but just moving things around. Okay, so the next thing I'm going to do is recall that I want to show you that Hamiltonian has something to do with time evolution. Right, so I want to invoke my Schrödinger equation at some point, but to do this I need to prepare my formula. So in order to do this, I'm going to rename my variable. So I'm going to substitute t, right? I'm going to rewrite this as t plus t prime. So in other words, t minus t prime, I just say that this is just t prime. T minus t0 is just t prime, right? Like this thing over here. Okay, t naught still the same, but now what I got is the t substitute into t plus t prime now. Okay, and then this is a summation from 0 to infinity, 1 over k factorial. So this is just t prime, but it's to the power k, and then this thing is still the same. So this is just differentiate t0 k times of my function. Okay, so again, not doing anything special, just substitute. So I just plug this in, right? Nothing special. But what I'm going to do next is, well, this one was our position wave function of my state at t0, right? And there's a ket over here. So these are differentiating with respect to t, and none of this depends on x. So my x is independent of t, so I can move the ket outside. Okay, so I move it here. So I move it here. This is because it's independent of t. And then the rest are inside. So the rest is summation k from 0 to infinity, 1 over k factorial t prime. All these are k times. So I'll just lump them together. Okay, I'll just lump them together. And then this is acting on t0. Okay, so this is so now we can start to see that this is something like a time translation already. Okay, in fact, let me just change this. Let me rename a dummy variable. So the t0, let's just rename this as t, right? It's just a renaming. And in fact, both sides are arbitrary x ket. So the x bar, I just remove this. So I'm just left with t plus t prime. And then I rename t naught to t, so I just remove the subscript 0. Right? So t prime is still t prime, so t prime to the power k. And this is just differentiating t, k times, and psi of t. Okay? So you notice, right, that this thing over here is an operator. Right? This is an operator because it does something to the state on the right. Okay, but what is the effect of this doing? So it does something, but it just is equals to this state. So it just gives me the state, but at a time t prime later. So this is what we mean by generating a time translation over here. And then you look at this thing. Doesn't this remind you of an exponential series, right? Because if you remember the Taylor series for Ex, right, is sum from k to infinity 1 over k factorial x to the power k. Okay, but this is almost the same, except this is a derivative that you are supposed to differentiate. So it's almost the same. So let us try to investigate what is actually going on. Well, first of all, this is differentiating my function k times, right? And we know how to handle this. Okay, because this is the Schrodinger equation, right? So if you recall the Schrodinger equation, what this our Schrodinger equation says. So IH bar d dt psi of t is the Hamiltonian acting on this, right? So let me just make it more clear. If I bring the IH bar to the other side, 1 over IH bar h, and this is acting on psi of t. Okay. In fact, if I differentiate this another time, and we assume h is constant, well, it might be a function of x, but let's assume h is independent of t, so that if I differentiate, the h is still there, but I'm just differentiating my function like this. Okay, but this is the same as this, so this is actually 1 over IH bar h, and then 1 over IH bar another h psi. Okay, so basically the second derivative of my function is just 1 over IH bar h square acting on this, right? So this second derivative. So now we know what to do with this already. So if I differentiate k times, it's just the Hamiltonian acting on this k times, right? So generally, if I differentiate my wave function k times, it's just 1 over IH bar acting on my Hamiltonian k times acting on my state. Okay, so therefore I know what to do with this equation already. So therefore t shifted by t prime is equivalent to saying this is a series of 1 over k factorial t prime to the power k, and then differentiating k times, it just means 1 over IH bar k times. Make sense? Okay, so this whole thing is to the power k. So let me rearrange this in a little bit more, right? So this is 1 over IH bar, and to make it look more familiar, right, 1 over I, again, always remember, is just negative I upstairs. So if I rearrange this, I am just going to get minus I. H bar is still down there, and then H Hamiltonian, and then there's a T prime, and all these are acting on the state k times. Okay, the T I can move anywhere I want because T is just a number, right? It's not an operator. There's only one operator here, and it's to the power k. Okay, so this is an operator acting on the state. So this is what we define. Remember the video of 3 blue 1 brown earlier. What does it mean by taking e to the power of a matrix? Doesn't make any sense. It doesn't. It just makes sense through here, right? We purposely call this, we define, because this formula is similar to the exponential series. So we define this as the exponential. I put in quotes because we are not taking e to the power here. It's just an operator, right? But it's an infinite series of the operator exponential of what? Exponential of this thing. So I of this thing over here, right? Constant times operator is some operator, so it's exponential of this operator, right? So we so that means what we have found here is the time translation of this is like taking e to the minus I h t prime over h bar acting on the state at original time t, right? So that means if I take the exponential with t prime over here, I'm shifting the system forward by t prime seconds, right? And this is what we call the exponential, right? It's just a short form of saying this operator. So this basically just some operator. So this is what it means by time evolution. Okay, and it depends on the Hamiltonian, because the physical, the system, right? It's what is the Hamiltonian here? It depends on the system. So for we have solved different problems before with different kinds of Hamiltonians. Does that make sense? Okay, so to reiterate what we have found just now, let's say I got an initial state, and my initial state is at time t, right? So this is my initial state, and then if I evolving this forward, that means this is, if I operate this by this t, here, so it means that I got t plus t prime for this t over here. So this is what we call the unitary evolution. The reason is because the operator is unitary. If I take e to the I h t over h bar, right? Unitary means operator is equals the dagger times u is identity, right? So if I do dagger I h t over h bar, so this will become plus I h t over h bar e minus I h t over h bar, and this becomes the identity matrix. So why this is equal to this is actually I'm skipping a lot of steps. So this explanation is not rigorous, but it's true. Because for numbers, something to this power multiplied by the inverse power, they cancel each other, they become 1, right? But this one is just a way of writing operator, right? This is just a way of writing operator. So operator this times this is actually not immediately clear why it should be an identity operator, right? Not so this is for operators, right? But it can be proven, just that we probably shouldn't waste time to prove it here, and it will be proven in more detail for certain math courses, I think in analysis or something. So let's see if there's any questions. How to use it? You mean this E thing, is it? Is that a question? How to use it? Well, I guess now we take a break, but when we come back, I will show you what this means. So how to use this. We will use this a bit more further later in chapter 7 as well, right? When we go to the Heisenberg picture of quantum mechanics. But yes, in any case, now is a good time to take a break. So let me stop the recording, that will melt your brain, right? It's just manipulating what we already know, and then we kind of get a new insight. It is something that we call a unitary evolution. Okay, so in this sense, right, you see like a quantum state evolving. So quantum state evolving, it means that it is evolving under a unitary operator. So this is why if you ever read any other things related to quantum physics, people always mention unitarity, the concept of unitarity a lot. Even when we talk about the black hole's Hawking radiation, there was a Hawking, one of the paradox about this phenomena is the information paradox, is because if you look at the initial state of the black hole and the final state after the black hole has evaporated, if you look through the details, the evolution is not unitary. But we derive the Hawking radiation paradox basically using just the quantum mechanics. We should be unitary. So there is something that we still haven't fully understood about this yet, right? Is unitarity preserved during the Hawking radiation or not? Okay, so if it's not, then like where does the information is being encoded and things like that. So the concept of unitary evolution is important. So in some sense, you can see that it preserves information if you look at from the information theory point of view, which we are not doing now. So so just some knowledge, right? That just to tell us that this is something to do with a very fundamental concept in quantum mechanics. Have I started recording? Yes. Yes. So yeah, just now I was saying, right, is previously what we did was we do separation of variables. We separated the time part, and we did separated the time part in something like an exponential, right? But that part is true. Is when we separated it, is an exponential of a number. This is an operator. Okay, so we separated in the operator, but now what we're doing is, we are studying this a bit more closely, and now what I'm going to do is I will connect this to what we did on the separation of variables. Okay, and to do this, right, should I mention this? So let's mention this last time, right? So last time when we got initial state, right? So let's say psi at time 0, and then at time t, it becomes E minus IE t over h bar, right? Of this initial state. But this must provided that this must be the eigenstate of h, right? And then of this same initial state. So that was what we did last time, right? We separated. Yeah, correct. That was the eigenvalue, and the state must be eigenstates of h. So that means we needed to solve the time independent Schrodinger equation is basically the equation to find eigenstates and eigenvalues. So now we can try to understand from what we have just learned, what is the context. So we got the exponential operator, right? So exponential operator of I h t over h bar. So this is our exponential unitary evolution operator, and this is just right, just to re-emphasize, it makes no sense to take e to a power of an operator. What does that mean? It doesn't mean anything. This is just a notation. It's a short form way of writing this series, right? So it's just 1 over k, and then it's negative I over h bar ht k times, right? So it's just a short form way of writing this. Okay, so to connect to what we did in chapters 2 and 3, we shall act on the eigenstates. So what happens if this operator acts on eigenstates of h? Okay, so what are eigenstates of h? So eigenstate of h, let's say I got an eigenstate of h, let's call it E, right? And because it's eigenstate, what this means is I got an eigenvalue, and the eigenvalue of h just means the energy of the system. Okay, So what if this operator acts on these eigenstates? So let's find out, right? So EIHT over H bar acting on EJ, what does that mean? It just means that this series acting on the eigenstate. So it's this series 1 over K factorial I over H bar HT K times acting on EJ, right? So again, we are not really doing anything special. We are just manipulating, the only new thing is just we manipulate things in a way that we didn't do last time. Like for example, what I'm going to do now is I just shift IH bar T here. I keep it to the power K, and then this is H to the K, so HK acting on this, right? So now we can, maybe you can sort of see what is going on now. This is acting on my eigenstate K times. So acting on eigenstate K times, I just get my eigenvalue out K times, right? So 1, 2, 3, 4, keep on repeating K times. So it's just back to EJ, right? So what we have found is, this is K0 to infinity. So this one is no longer an operator. 1 over K factorial minus I over H bar T to the power K E J to the power K E J. Okay, so if it's still not clear, let's just write one more step. Right, so everybody here is to the power K. So this whole thing here is to the power K. And let me just rearrange this. And this whole thing is multiplied by my state EJ. So now this is no longer an operator, right? This is just a number. And if it's number, then this is the usual Taylor series. So this is now an ordinary Taylor series of numbers, right? They are not operators anymore, right? So if it's just a number, then yes, even if you show this to someone taking calculus 2, they will tell you that it is e to the power of I e j t over h bar. So if my unitary evolution operator happens to act on an eigenstate, so the important point here is it must be an eigenstate of h, right? If it's not an eigenstate, then you cannot really do this. But yeah, what we have found here is we have derived the result that on the left hand side is exponential I h bar t acting on eigenstate. I can just replace this with the corresponding eigenvalue. Right, so I replace this into this. So even though this equation looks like, of course, it looks like nothing special, but actually it's not, right? The reason why this operator can suddenly change into eigenvalue is because of all this calculation, right? And it is because we are acting on an eigenstate of EJ. So for any random state, whatever different, if you change this to some non-eigenstate, then cannot anymore. Okay, so it must be for eigenstate. But in any case, what we have found is I have re-explained why at the beginning for Larmor precession, right? Where was it? Starting from initial state, right? This is an eigenstate of h, right? At any time t later, I just exponential IET, right? Then for this, I exponential of the corresponding energy over here. Okay, so yeah, basically what we have found is if the initial state it is an eigenstate of the Hamiltonian, then let's say initially EJ, so the unitary evolution so this is at time 0, and then this is at time equals to t. It just gives me a negative I e j t over h bar e j, right? So this must be the eigenvalue of this, right? Must be the corresponding eigenvalue. Okay, so now we are ready to get a more general result. If it's just one state, then yes. Then what if it's a linear combination of eigenstates? Then the same thing works. right? So let's say my initial state at time 0 is C1 eigenstate 1 plus C2 eigenstate 2. Yeah, don't know how many, right? Could be n, in fact, it could be infinity, depending on what is your initial state of the system. Then unitary evolution will give me my state at time t as so we did this for one term, so for each term we'll have the corresponding evolution. So I got minus I E1t over h bar, this is the first state, and then C2e minus I E2t over h bar for the second state, and so on and so forth, right, until n, I E n t over h bar E n. Okay, so that is how we work. So the important thing to remember is, see, this is not a linear, this is itself not purely an eigenstate of the Hamiltonian, so you shouldn't write this as I E t over h bar psi, right? Because what will you put here, right? Because it's a mix, it is a combination of different e's. So for this eigenstate I got this e, for this eigenstate I got this e, and so on and so forth. Okay, so now back to the original question, or the title. We call the Hamiltonian the generator of time evolution, right? And the reason, and notice that all this is because of the time evolution. Means is the physical evolution of the system, and the physical evolution came from what? We derived this from the Schrödinger equation in the first place, right? So yeah, let's make this observation. All this happened because of the Schrödinger equation. Right? So we needed to use this formula to substitute the Hamiltonian inside, right? So actually it depends on the Schrödinger equation. And so this is why the Hamiltonian, so this part is special. So this part is what we call the generator of time evolution. Right, so H is the generator, and from the generator you can construct minus I over h bar generator, and then for any scalar constant t, yeah, so basically you just get minus I h t over h bar, and this will give me your unitary evolution operator. Right, sometimes we call this ut. So I think we will do this in a bit later also. So sometimes we use the symbol u because it stands for unitary. So IHT over h bar. Okay. So this is the thing that yeah. So to help us imagine something, I guess this is like the play button. Right, so this is the thing that makes the system will run forward in time. Okay, so yeah, so that is yeah, basically just a time evolution operator. So this is responsible for running the clock forward or running the system forward. Okay, so that is it about the Hamiltonian. Is there any question? So now we switch gears a little bit. We go to the next topic, and it might feel a little bit like a difference from this part, but it will be related down the line. Okay, so it's just in preparation of what we are about to discuss a bit later. And what I'm going to talk about next is basically let us continue the story of the Stern-Gallac experiment. So what we're going to do is we are discussing mixed states and introduce the concept of what we call the density matrix. Again, this sounds like more fancy terms, but you will see how it comes, right? So hopefully it will just come in naturally. And let us, well, to begin, let us remind ourselves what is the Stern-Gallac experiment. So let us consider the Stern-Gallac experiment again. Okay, so hopefully your brains are not melting. Just doing the same, nothing new. This is just a recap. For the Stern-Gallac experiment, right? The two outcomes we have studied in much detail, right? Spin up and spin down. And let's say I have a beam that is in this state. So I have a beam that is in this state, and then you do the sigma z measurement. Or in fact, now we know that Sz is h bar over 2 sigma z, right? So now we know everything of this story already. So if we pass through this inhomogeneous magnet, the beam will split, right? So this will be going here. And if this is A, then we can even calculate the probability that an atom will go this way to be modulus A square. And the other outcome will be the beam coming down. And the corresponding probability will be modulus B square. So obviously this plus this must be equals to 1. These are probabilities. Okay. So yes, we have spent quite some time since chapter 1 to talk about this. Quantum state is not determinate, right? A cat can be alive or dead. We don't know until we do the measurement. This is a quantum effect. We don't know until we observe it, right? So like the Schrödinger cat experiment. So that means this is, to re-emphasize, let me write this. This state that I write here is a quantum superposition, right? Superposition between up and down. So I'm just repeating familiar things, but emphasizing a few concepts. This is a new name that I will introduce, right? So this quantum thingy, right, whether the cat is alive or dead, but which we don't know, but there's a 50-50 chance, that kind of thing. So reality is undetermined until we do the observation, right? All those weird things we had discussed chapters 1 and 2. We shall call this the pure state. Okay, because what I'm going to do next is it will be clear in the following, right? So this is a quantum state of 1 plus quantum state 2, quantum superposition. Okay, and it's a superposition of state up and state down. But of course, right, there's a second way to consider this of two possible outcomes. Maybe you can say instead of like it's a being quantum with neither up nor down, maybe I just have a bunch of up spins atoms here, and then a bunch of down spins atoms here, and then I just like mix them together, right? Doing this is not a quantum effect. Do you agree? Right? It's just the same as when you're making coffee, right? So when you're making coffee, you take the coffee, and then you take the sugar, and then you put in a cup, and then put water, and then you stir. Nothing quantum about it, right? But you are mixing the thing, right? You're mixing the two different things into the same system. So that is what we want to discuss next. What if the mixture is just a mixture? It's not really quantum, right? So let's consider this. So what if we do this? Okay, so let's say I take up spin, okay, and then I got a beam of down spins. So I got a beam of up spins, a beam of down spins, but then I just combine them. Okay, then if I combine them, well, so now so whether it's quantum or not, what we do know is inside this beam consists of atoms. Some of them are this, some of them are this. So if I pass through the magnet, then yeah, some of them will go up, some of them will go down, right? So now we got the puzzle. We know what to do for the quantum case, right? We know what to do for the quantum case, but what is the probability of measuring this, right? And same story here. So the thing that goes down, yeah, sure, but what is the probability that is going down? Okay, so what is the so right now, right, what is actually happening is, yeah, this is we are kind of going backwards. This should be easier to understand because this is just not quantum mechanics, this is everyday life. It's the same as mixing 5 blue color marbles and 10 red color marbles. If you mix them together and if you randomly choose one out, what is the probability of getting a red marble? What's the probability of getting a blue marble? Right? In fact, you guys are taking the prop and stats class things, right? So it's basically this situation, isn't it? Right? It depends on how much beam is here, how much beam is here. So let's say this beam, is W1%, right? And then this beam is W2%, right? Maybe this beam has many atoms. This beam has just a few atoms. So when you mix together, the full beam is basically just the whole beam is 100%. So if I do this, right, then we expect that this should be, the up one should be because of W1 and the down one is because of W2, right? It's like, yeah, 5 blue marbles and red and 17 blue marbles put together in a bag mixture, and then you take one and red. So at a random atom, what's the chance that it will go here? What's the chance that it will go here? Okay, so this one, yeah, this one is this mixing of the state, right? And to get this beam, this one is not like just, this is not really like a quantum superposition, right? So this part here is not exactly quantum. Okay, so if you read this later, just to remember, this one is like coffee, and then sugar, and then you mix it, right? So yeah, it's perfectly fair that this thing might happen, right? You just literally join the beams. So we need to develop a theory of how to calculate these results, right? In other words, we need to develop a theory of mixed states. So this is what we call the mixed state, right? So just now, in contrast, what we have earlier, so the original one, when we consider quantum mechanics, most of the time in quantum mechanics, we consider pure states. But this one is, yeah, just mix, right? So you still get some mixture, you still get some probability. And the probability is more closer to your normal probability and statistics kind of things here, right here. But here, yeah, the quantum one, we develop all the rules in the 5 postulates that we say in chapter 1. We know all this already. So what if it's doing this? Okay, so that is what we want to do, right? In fact, if it's a mix, then you just use yes, so maybe you can answer me already, right? If this is a normal mixture, then it's the same as a statistics problem or a probability and statistics cost type of issue, right? So everyone knows how to do that already. But the things become more complicated if it's the general case, right? So let's say now I got a quantum superposition here, giving you this beam, and then another quantum superposition here, giving you another beam, right? So this part is easy. The W1 is also like kind of, yes, what is the proportion of this beam and proportion of this beam? Sure, but what is this state now, right? So yes, this part you use statistics, no problem. This part we already done this in chapter 2, no problem. But what if I combine both situations together? Right, quantum superposition, and then you mix them, right? So yeah, so this is the problem that we want to handle now. Okay, so in order to do this, right, so that means if let's say if I measure sigma z, what comes out? Okay, so yeah, interesting question, right? No, they're not entangled. Yeah. So for the moment, yeah, although there's one assumption that we make, so assume that the atoms in the beam don't interact with each other. Yeah. So they might become entangled if they interact with each other. Yeah, you're right. So you're on the right track here. But we haven't learned about entanglement yet, so we cannot handle that problem yet. So, but we assume the ideal case, they do not interact with each other. Okay. So, but generally it's true, because when quantum system interact, entanglement almost always happens. So that is one of feature of condensed matter physics, and one of the source of many properties of condensed matter systems. So yeah, so now this is what we want to do now. We want to develop a theory to handle this situation. So this is what we want to do now. The first thing that we want to do is we can't really write a ket to represent this state, because once we write a ket, right, it just becomes like a quantum superposition. So we can't write this to represent a mixed state. In fact, what we need to do is we need to represent states using operators. So to represent states, we need to express as ket bra. Okay, so partially the reason why every time I solve a question, I always go to the ket bra form. It's kind of a practice. So because here we cannot avoid, because if sometimes you can always convert things back to a matrix, but sometimes it's not very convenient, because the matrix can be very, very large for certain systems. Okay, so yeah, so we need to use operators instead of just kets. So if we just kets, then it's just a pure state quantum system. Okay, so let me remind you what is a ket bra. We can always build a ket bra using two kets. So given ket A and another ket B, right, I can build a ket bra is, let's say, A, B, right? So you just flip one and then multiply them in the opposite way, right? So this is the same as a column vector times a row vector, giving you a matrix. Okay, and also, well, if I take a ket bra and then if I take the Hermitian conjugate, it is just flipping. So it just flip B into A, right? So this one is also another operation that feels like playing Tetris. Okay, and another thing to remember is this: a ket bra is always an operator. Okay, and operators can be multiplied together and added and subtracted. Right, so let's say if I take A, B, okay, and then if I take another one, alpha, beta, and then I just get a new operator, right? Basically another ket bra, right? So this one I can add them, and then I can multiply them together, right? So let's say A, B multiply by alpha, beta, okay? So this is why the ket bra notation is so nice. It's just A, B, alpha, beta, right? So you just put everything together, and then this one, the moment you do this, it becomes a number. So if it's a number, I can move it out. So if I can just move it out, it's just B, alpha, and then A, beta, right? So this is just a scalar number. This is a ket bra, so this is an operator. Right, so operator times this one is basically like a matrix times a matrix, giving you another matrix at the end. Okay, so you can do all these things with the ket bra operations. Okay, so and then also, in fact, this one is just a more complicated version of this because they are operators, right? right? Ket bra. Remember, what does operator do? They eat a vector and spit out a new vector, right? Here is a ket. So operator eats a ket and then spit out, or some of you prefer shit out, a new ket, right? So let's say I got a ket AB, right? So this is an operator. If I add this on something, right, it just becomes A, B of that something. This one is just a number now, so it's just a B psi. Okay, right, so this one is basically just a scalar number and then times a ket. Okay, so even though we introduced the ket bra, it looks like very fancy, but I guess the way to play around with it is pretty intuitive and straightforward, right? Sometimes it might feel fun to move things around like this. Okay, so yeah, so hopefully it's not too bad. But what I'm going to do next is to define another new operation which we call a trace. Okay, before we are able to do the mixed state, so we need to define. What time are we now? This operation is called the trace. Okay, what does trace do? Well, if I have a ket bra, okay, I just change this into the this, right? So basically I just reverse the order and multiply them together. It becomes a number. So an operator turns something into a number. Okay, and then notation is the trace, TR is equals to BA. Okay, maybe you have heard the word trace before. It's familiar, right? Because when you're doing linear algebra, you also take the trace of a matrix. It's the same thing actually. So this is what I want to say next. This is similar, the trace of a matrix, right? Why? Because let me show you. Firstly, let's say I got a ket, right? And usually we always write the ket as a column vector. So I got A1, A2, dot dot dot. Let's say AN, right? And then let's say I have a bra, the bra B, and B we always, well, at least I tend to, my habit is to write as a row vector, right? B1 conjugate, B2 conjugate, until Bn, complex conjugate, right? So when you do the ket bra AB, right, you're basically just taking the column vector multiplied by the row vector, and you end up with an n by n matrix. Okay, it's just A1B1 bar, A1B2 bar, right? And then all the way until A1BN bar. Then the next one will be A2B1, A2B2, dot dot dot, A2BN, right? So all the way until the last one is ANB1, ANB2, and the last one is ANBN, and everything in between, right? So what happens if we take the trace of this operator? So when I say we take the trace of ket bra AB, by the definition we say that it's actually BA. And what is BA? BA is the inner product. So the inner product is just basically just A1B1 plus A2B2 plus ANBN. And yeah, it's basically the same as summing up the diagonal elements of a matrix. Alright, so it's actually the same thing that you do in the linear algebra. Right, so even though I say I define something new, but it's actually, you have already done this before, just taking the trace of an operator. Any question? Shitting up makes it less pleasant to work with. Yes, correct. Because, yeah, it makes sense, right? Spitting up better, because just now we did something like this. So the the next Hamiltonian will have to eat whatever the first Hamiltonian ate out. Right, so you got this. Yeah, I guess spitting out is better to say. So now that we got the trace, we need to be doing the trace quite often later. And this one is also something you probably learn in linear algebra also. One of the properties of the trace operation is it is linear. So the trace operation is linear. What does linear mean? Well, let's say if I have an operator A and then plus another operator B, right? You just get a new final operator. In fact, I got scalar multiple times this operator times this. What you get is the scalar, you can take it out, right? And then it's just the trace of A plus B times the trace of B. Okay, so this is what we mean by it's a linear operation. Okay, so now we are ready to kind of handle the mixed states already. So yes, let's get started. Now we have the tools. So let's see how to build an operator representing a mixed state. First, we need to make an observation. Let's consider state psi. So this is going to be pure. Let's look at the pure one for the moment, right? And let us say an operator let's call this S, right? So it's kind of like reminds us something with the spin, right? So now if I have this, right, let me do the ket bra version of this state. So this is going to be psi of this, right? And then I got an operator S. So if I act on the state, what do I have here is S psi. Okay, now we notice this, right? Remember, the operator is something that eats a ket and gives you a new ket, right? So it's a new ket. Basically, what I'm trying to say is S thing is a ket. So now we do the ket bra of this, right? So S ket this is a ket bra, basically, right? Because I was convincing you that this is just one ket, so I can join this with another bra to give me an operator which is called the ket bra. And then let's take the trace of this. Okay, by the rules of the ket bra, this thing I move it and then I take the inner product. And what have we found? This is actually the expectation value of my operator S. Okay, so now that we see, right, now we look back at what we did. We are taking the trace of S times this, right? So this is the operator here, and now if instead of looking at this as one ket, we look at this piece like this. So this piece, when you do the trace with this operator, it gives us something about the system. Here is the expectation value, right? So what we can find is, yeah, so we notice that this state can give us information about the system. The expectation value. So in the example I'm showing you is the expectation value, right? And it's possible to get other information as well. Okay, so this thing is going to be important, and this is what we call the density matrix. Okay, but in this example, right, I'm taking one state. Remember, when I write it like this, right, it's just like you can do this in the original Stern-Galak experiment. This is just a pure quantum superposition. So the density matrix, so for now we define the density matrix of a pure state. Is, we call this rho, right? So this rho will appear many times. It's an important quantity, the density matrix. So if you attended the main campus talks or things like that, right, you have seen rho here and there, and it refers to the density matrix of the system. Okay, so yeah, so in the last 4 minutes, let us give an example. By the way, any question, or is your brain melted already? So if we have time at the end of the course, right, this reminds me, if we have time at the end of the course, we will discuss a bit of entanglement, but for fun, it will not be in the exam. So let's work out an example here, right? So let's say I'm given this pure state. This is just a normal, well, yeah, by now we are used to these kinds of quantum superposition. We just want to find the corresponding density matrix and find the expectation value of sigma z. We know how to calculate this using our original methods, but we now just practice doing it using density matrices. Okay, so in this example, 7.2.1, the state that is given to us is 1 over root 2 up minus down, right? So this is a state that we handle this state quite often already, but now what we want to do is to find the corresponding density matrix of this state. Okay, so this one is again nothing special. You just do directly what is shown here. That means one of them is a ket, so you write the ket here. The other is a bra, so you take the bra here, and then you just expand. So nothing special about it, it's just direct calculation. Up times up, so it just gives me up up, and then up times down, so minus up down, and then down up, and then down down. That's it. This is my density matrix for this pure state. Okay, and the next thing that we want to do is we want to calculate the sigma z. We know, yeah, so we know how to do this, right? But now we practice using the trace method. So it's sigma z traced with the rho operator. Okay, so this is how you calculate using density matrices. So that means my sigma z acting on all of this, and the trace operation is linear. So the trace of sigma times this, something times this, actually I can take out the scalar, so it's just taking the trace of sigma z times up minus half taking the trace of sigma z up down minus half taking the trace of down up, and finally half taking the trace of sigma z down down. Okay, so this one it will just, so this one it just give me a up, so this it give me up up, and then this term is going to be 0, it's going to be 0, this term will give me a negative eigenvalue, and then half down down, right? So half minus half, the expectation value is 0. So we have done something similar. If you do this in the traditional way, you will get 0, right? Because the possible outcomes is +1 and -1. The probability of both is half. So the expectation value is exactly in the middle of plus and minus 1, which is 0. So that is why you get 0 expectation value over here. Okay, so yeah, exactly, now it's exactly 5:50, so it's a perfect time to yeah, so let's stop here and we shall continue on Monday. So hopefully we have some presentations on Monday. Besides that, we shall continue on this density matrix kind of things, and yeah, and that's about it, right? So we are nearing towards the end of the semester now. So let me stop the recording and I will see you next Monday.